This section is about applications of linear functions. So suppose a ball's descending at a rate of 20 feet per minute from an elevation of 1350 feet. Write an equation to model the balloon's elevation as a function of time. So I have a starting amount. This would be my b, and my slope, since it's descending, would be negative 20. So my equation, I'll use height and t for time. So the height is going to be negative 20t plus 1350. So the slope is going to be negative 20. So that means that you're going down 20 feet per minute. And then your y-intercept is 1350 because that's what you're starting at. So the y-intercept is 1350, or your starting height. Graph the function on your calculator. So in class we're going to talk about how we put this in our y equals, how we probably want to change our scale. So our scale would go, we're talking about scale on the x-axis being time for minutes, and then height. So I would have my y scale go up to at least 1350, so maybe 1400. So the y min would be 0, and the y max would be 1400. And the x min, I'd put 0, and the x max maybe will go all the way to, let's see, 200. So that'd be like 200 minutes. So graph the function on your calculator. It's going to look something like this. It's going to be a straight line going down. The y-intercept would be 1350. What is the height of the ball after a half an hour? So half an hour is going to be 30 minutes. So you're going to plug in 30. So it's negative 20 times 30 plus 1350. So that is going to be 700, I believe. So negative 600 plus 1350, 750, yep. So 750 feet for the balloon. Example 2, a candle is 7 inches tall after burning 1 hour and 5 inches tall after burning for 2 hours. Write the two ordered pairs to model this. So this is when I have to be careful about independent and dependent variables. In this case, remember that time is the independent variable. So I'm going to write it 1 hour. After it burns for 1 hour, it's 7 inches tall. And if it burns for 2 hours, it's 5 inches tall. So if I write a function, I have 2 points. So remember, you can write an equation of a line given 2 points. So first I'm going to find the slope. So the slope is going to be 5 minus 7 over 2 minus 1, which is negative 2 divided by 1, which is negative 2. So the slope is negative 2. So in point slope form, I can take any of these points and a slope and write it in point slope form. So it's going to be y minus 7 equals negative 2 times x minus 1. Now I'm going to actually solve for y when I write my linear function. So I'm going to do y minus 7 equals negative 2x minus 2 and add 7. So y equals negative 2x plus 5. Oops, actually I noticed a mistake because I noticed that was kind of weird for it to start at 5 when after it's burning down. It burns down at 1 hour 7, so I can see my mistake right here. This would be plus 2 right here. Okay, so this should have been a positive 2 because negative times negative is positive. So add 7, so it's going to be plus 9. That makes more sense. How tall will the candle be after 3 hours? So I'm going to plug in 3 for x because x represents the time. So it's going to be y equals negative 2 times 3 plus 9. So y equals 3, and my units are inches. Okay, scatter plot. So a scatter plot is when you have different data points when you're plotting different data points. So some scatter plots can look like they make a line, so that then we would do linear regression or do a line of best fit. So you can have weak correlation. So weak correlation means it's kind of hard to see the relationship. It's hard to see a line. You can have strong correlation. So see how this is tighter together to make the function, and this is tighter together to make a function. These are both strong correlation. So you can have positive correlation is going to go up from left to right. Negative correlation is going to go down from left to right. And then no correlation means it's difficult to even to make a function. So a woman is considering buying a 1999 vehicle for $4,100. Create a scatter plot below of the data. So what we're going to do is actually we're going to create a linear model on our calculator. So what you're going to do is find the stat button on your calculator and then slide over to edit, and we're going to put the model year L1 will be 2000. So the points will be, I'll do a few of them, and then I'll stop it and put it in my calculator. So the points will be 2000. So 2000 you got 5784. And then in 2000 you also got 5435. And then in 2001, so you have to put 2001, it's 6810. So continue to put those in. So I have all these points in, and there actually ends up being 10 ordered pairs because there's 2, 4, 6, 8, 10. So after I have these in, after I edit these, I go back and press the stat button. So press the stat button again, stat, and you have choices for edit, calc, and test. So you want to slide over to the calc. So slide over to the calc, and then you have different choices for calculus, for calculating. So go to number 4, which is lin reg. So that's going to be linear regression. So we're doing our calculating our line of best fit. So select linear regression and enter through until you get an A and a B value. So my value for A, everybody should be the same, but I have A equals 1306.9, and then B is negative 260.8342.4. Okay, so the A represents the slope and the B represents the y-intercept. So I'm going to write this as an equation. So the equation, this is the line of best fit, is 1306.9x plus or minus 260.8342.4. So is $4,100 a fair price for a 1999 vehicle? So you can see that as the years go up, the price goes up because these are newer cars. These are older cars. So to figure out if a 1999 vehicle would be $4,100, what I would do is plug in X, let X be 1999, and see if we're close to 4,100. So I'm going to plug that in. So I do 1306.9 times 1999 minus 260.8342.4, and I get 4,150. So actually, yes, 4,100 would be a fair price because it's close to 4,150. So I'm also going to link a video on how to do a linear regression. So again, this one, you're going to want to put these numbers in your L1 and these numbers in your L2 and come up with the linear model.